Your team is wasting many hours every day searching through documents and files. What if they could find an answer instantly and accurately from your entire knowledge base? So imagine a customer representative that can reply to a client in 3 seconds instead of 45 minutes. A sales team that can close a deal because they find product specifications immediately. Or an executive that can make a decision with real-time policy information. This is retrieval-augmented generation. I'm going to show you how to build the full system for your business. You will understand how RAG works at a high level, and you will see the 2 big pipelines, ingestion and retrieval. You will see how to take a user query, search through all your documents, and find the exact right information that you need to reply to this user question. I'm also going to show you how reranking works. With this, you'll be able to convert a system with a good accuracy to one that has excellent accuracy. And all this is going to be a very practical demo. All the code that you will see in this video is open source, so you are free to take it, modify it, and play with it. You will find the link in the description. My name is Dani Fulla, and I'm the co-founder of Flowhog. We do not only help our clients understand where in their processes makes sense to put AI, but also we build custom AI solutions for them. So if you're a business that wants to integrate AI, but you don't know how to do it, I will leave a link in the description that you can use to get a free audit, and this will serve you to understand what processes in your business make sense to automate. Great, so the idea of the video is to have some theory, but also to have some technical explanations. So on one hand, we are going to follow this PDF that contains our guide and the different slides with the processes that we are going to see. And then after each slide, we'll go to our code that actually you can find it it's over here. So just make sure you pull the AI Agents tutorial repo that I will leave a link in the description. Just get into the custom RAG folder, and here you'll have all the code together with the slides. Great, so let's start by explaining a bit of RAG. Very likely you have all heard this concept and you all know what this is about. Almost any application that you see out there is using a RAG. And this is because the LLM models that we are using are trained and have knowledge until a certain date. And sometimes they don't have access to our private data. Actually, they do not. The idea of this video is to create a system that is going to allow us to retrieve information that we have about our company. So this is private information. And to provide it to an LLM so that it knows how to reply to our questions. And with this, being able to access to our information instantly and accurately. So this is the process that every RAG follows. So first of all, we have a document ingestion. And this is a one-time thing that you do for all your documents. So basically, you take your documents, you convert them to text, you extract chunks, like pieces, and then you get the embeddings of these chunks. I will later get into these concepts and explain it more in detail what they mean. And finally, you store them in your database. So it's very important, as I said, this is a one-time thing. You only do this one time for your documents, and after that, unless you are changing your documents, you never do this process again. On the other hand, when you are doing context retrieval, so it's the second phase, you have a question and you want to extract the information that could reply to this question. You go through these 3 steps. First of all, you do some question processing or query processing. Then you do search on this database that you previously created during the ingestion. And finally, you do some kind of reranking. So it's basically after retrieving certain pieces of text that could potentially reply to the user query, you pass them through another model that will allow us to say, okay, out of all these pieces, which are the ones that actually contain the information. And finally, once you have all the context that can be used to reply to the user query, you just pass it to an LLM to create the response that we are looking for. All right, so let's get to the next step. So we are now going to see the first pipeline that is about document ingestion. Our goal here is to create a knowledge base about your business. And more importantly, that this knowledge base is structured. Because right now you have all your documents in your PC, but it's a mess. Okay, you have many formats, you have it in different folders, and if you have it like that, it's impossible to extract the information and pass it to the LLM properly. The document ingestion is made of 4 different sub-processes. First of all, parsing. You have to take all these documents that are in different file formats like PDFs, Excels, emails, Microsoft Words, and convert them to text. Once you have this, you're going to split it into chunks, as we said. Then we're going to extract the semantic, like the meaning of each chunk. And finally, we're going to store this in a database. Anyways, let's get to each of the different processes. And here we are now going to jump in the code, and you will see with a real example how each process works. For the parsing, as I said, you have many documents. Very likely you have folders like this with documents in different formats, okay? And the idea is that for each of these documents, we're able to extract text in what it's called Markdown format. Now here we're using Markdown format, that is a format very used in the web, but actually you can use whatever format you want. Maybe you want to use just text without the Markdown style or whatever. This is up to you. The only thing is that when using Markdown, it's easier for the LLM to understand if some piece of text, it's a heading, or if it's a paragraph, or if it contains some stylings like bold or cursive. And this way, the LLM knows that, for example, that particular word is important. So let's get to our code and let's try to run our system. If you clone the repo, you are going to see something like this. As of now, just ignore the front end and let's focus on the backend. Inside the backend, let's go to app and rack. So we will see each of the subprocesses that I mentioned before, like chunking, embeddings, parser, and reranking individually. And after that, we're going to combine them into one unique pipeline so that all this process happens at once. Now, just for exploration purposes, we'll go through each folder and we'll run a small example so that you actually see what's the input and the output for that specific subprocess. So let's go first to the parsers, so that remember it's the first step in our ingestion pipeline. So inside this class, we will use PyMove-PDF for LLM to just get a file, a PDF file, and convert it to text. So actually, here I'm just defining some functions that use this library. But this is just for the PDFs. Here, what you would do is to create a parser for each different file format that you have on your PC. Like one to convert emails to do Markdown, one to convert Microsoft Words to Markdown. Actually, there are plenty of libraries out there to do this. Here I'm using PyMove-PDF for the PDF, but you could also use doclink that I used it in my previous video. Or there's another one very famous that it's unstructured.io. Here it's just a matter of trial and error. Just keep playing with different libraries and see what's the one that best suits your use case. But in any case, here we have defined this class, and inside examples, we have this script that actually is going to take one document from the documents folder, and this document will be converted to Markdown. Actually here, I've already done this operation. This is why both the PDF and the Markdown, but actually, for example, let's remove this one. And here I have the annual report of NVIDIA. So it's 181 pages and it just contains the consolidated statements for the 2025 fiscal year. What happens now? We cannot store this text properly because this is just a PDF. So we need to extract each text and put it to Markdown format. So let's do this. Here, if you go to the commands.md, here I have the different commands that you can run. And here, let's go to the parse PDFs. And this is the command that we are going to run to parse a specific PDF to Markdown. For example, I'm going to copy this. Just make sure you are inside the backend folder. Here, just paste this and replace the file for the one that you want. That is actually, no, let's keep this file. Let's select, for example, the annual reports. Remember that the output that we want is the markdown.md. So now the script starts to run. It's just going to take this document and it's going to use the class that I showed you before, the PDF parser, and just call these functions, parse to Markdown and save to file. All right, and now it just finished. This new Markdown folder was created. So this is cool because now here we have a huge file that actually contains all the data that it's here. For example, we try to look for this, just some text. Here we'll see it's our executive. And the nice thing is that it's able to detect the titles and subtitles. For example, here it's putting on bold this subtitle. And also, for example, here you see it's using different headings for the different sections that it detects. Having said this, you will see that sometimes PyMove PDF, it's unable to properly parse the document. For example, for this page, this is an image, and very likely PyMove PDF hasn't managed to properly convert the image. Yeah, so here, for example, normally when you see these huge gaps is because there was an image there and wasn't able to parse it. Let's see if we find a table. For example, actually I have here this quarterly presentation, and all right, here you see again some graphs and table. And if we go to the quarterly presentation Markdown, that I already did this process before of parsing. So here you see that it has converted this table over here to this format that actually it's quite good, to be honest, because this is a set Markdown format, and an LLM will be able to interpret this as a table with the different headings. But I have to be fair with you, many times this is not the case. Converting tables can be a bit difficult. So here it's just a matter of trying to adapt your parser to the type of data that you are working with. So if you're working with a lot of tables, very likely you will have to use another library that is better for parsing tables. But if you're working with more text, maybe this one is fine. If you're working with images, maybe you have to use Dockling. You just have to see what's the data that you are going to work with, and according to this, you will build the different parsers that you will need to use. I think we can proceed now. So the next thing we have to do is to chunk it. Why? Because this is a huge text, and actually if this is more than, have a look, 18,000 lines, you cannot pass this to an LLM because you will explode the context. But even if LLMs are able to accept more and more context, your job is to make sure that you only pass the right context to the LLM, because otherwise it will get saturated and the accuracy of the responses will dramatically decrease. So imagine it's not the same asking the LLM, hey, what's the name of the professor of materials and science, and just passing this context to the LLM, and it will immediately say Persis S. Drell. But if you pass like this 17,000 lines, the likelihood that it's not able to reply properly, it's very high. Let's create the chunks. Here again, I have this folder called chunking. Here you have the Markdown chunker, that it's another class that I have coded. Actually, this one I have not coded it myself. I will leave a link in the description of an interesting article of a person that created this chunker using Node.js. So what I did was to convert his chunker to Python. I really like this chunker because it's what it's called a hierarchy chunker. So actually, what happens? So you can do chunking on many different ways. So, for example, you could be chunking this according to a specific number of characters, let's say 100. But the problem is that very likely you would split a sentence in half and you would miss a context. Ideally, what you want to do is to make sure that each chunk contains a context that it's not broken. And if you're able to also integrate inside the chunk the reference of where the chunk is located, the LLM will be able to answer better the user question because it will have the context of where this section is located inside the document. So in this Markdown chunker that I have here, every section that it's splitted, it will add on top an index. So it will say the document, the title, and the subheadings of this section. So for example, for every section inside notice of 2025 annual meeting of stockholders, it will take the specific chunk. So for example, here, power of attorney, very likely will take this. Okay. And then on top of this, it will add this heading in accordance with item, blah, 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 blah. And this way, as I said, we are adding more context to the specific chunk. So let's go to it and you will see it more clearly. So inside chunking, just go to examples. And here again, we have a test chunker script file that is going to allow us to chunk a specific Markdown file. So here, go to the commands and just take this command over here. You will run Python and just put the name of the file that you want to chunk. Remember, you have to put a Markdown file. So if you don't have the Markdown file, you first have to convert the PDF to Markdown using the parser. And once you have the document, that will be stored inside documents. Okay, this one. Okay, nice. And now the script has chunked the full pages into different chunks. And actually you have a total of 760 chunks. So here in the console, you'll see each chunk and the context. And remember what I told you, on top of each chunk, you will see the headings of where this section is located. So if we go inside chunking outputs, you will see the file itself with a different chunk. So the same that you're seeing in the terminal, you will see it here. Here we have a summary, like it has generated 760 chunks. So here you see that the chunk is this section over here until here. We are operating a dynamic. Here actually the chunk has been split in the middle of a section, so this is not optimal, but it's almost impossible to get every single chunk right. Still, let's focus on this one. As I was saying, the chunk starts with "we are building," so it's this section over here, and we have added the headings where this chunk is located. So you see GeForce RTX 50 series AI powered gaming. This is here, GeForce RTX series AI powered gaming. And inside this heading, we are in the section, we are building the essential infrastructure. And it's super important because this will heavily increase the accuracy of your system if you are putting a hierarchy of where each chunk is located. All right, so now we have the text split it into chunks, and now we have to get the embedding for each chunk. Now, what's an embedding? I'm pretty sure that you have all heard this word and everyone is using it out there. And it's very important to understand, first of all, why we are using embeddings. What happens? Traditionally, when you were searching in your database, you were using keyword matching. If you had a text that was talking about a king that liked apples, if you had a question that was, does our king like apples? You could easily have a match because the question of the user contains the word king and the word apples and likes. And these three words are inside the text that we have in our database. Having said this, just contemplates the ideal scenario, but it could be that the user uses different words. So for example, instead of king, it uses another term, for example, the husband of the queen, or instead of apples, it uses a red fruit. So with traditional algorithms, you would never be able to match the query of the user to the context that you want to get from your database. So this is where embeddings come into place. So what is an embedding? An embedding, it's not more than a vector that it has a fixed size, and normally it's around 1,500, depends on the model that you're using, but for the sake of simplicity, let's assume that it's a 1,500 size, and this vector, that it's just a set of numbers, represent the meaning of a text. This is going to allow you to know that the text is talking that the king likes apples. This text has the same meaning that the husband of the queen likes red fruits. It's not exactly the same meaning because a red fruit could be another type of fruit and not necessarily an apple, but the meaning is very similar. So when we convert these two texts to a vector, they will be very close, and they will be way more closer than, for example, another text that talks about a city. So you get the idea. And here I have done this representation. So for example, if you have the first chunk that talks about a king, when you take this chunk and you pass it through an embedding model, the output vector will be over here. So here I have simplified the vector. Instead of a 1500 length, that actually we cannot represent it in the space because we only have three-dimensional perspective, I have simplified the representation of an embedding into a bidimensional vector. So there are just 2 dimensions, okay? So imagine, if we represent this chunk that talks about the king, when we pass this through the embedding vector, we'll get, for example, that the king, it's over here. Now, if we now do the same with a second chunk that talks about the king wife, very likely the second chunk will be very close to the one that is talking about the king. You have to think that there will be still a lot of space between them, but you have to look at this from a relative point of view. Despite the distance between these 2 vectors could be large, if you compare this to another chunk that is talking, for example, about what type of fruits the king likes or dislikes, these 2 other chunks will be way more distant than the one that is talking about the king's wife. This is actually the idea of getting embeddings for each chunk that you have in your text. So now if we go back to our code, we go to the embeddings folder. That again, here I have an embeddings class that is going to allow me to create some vectors out of text. So here I will be using the OpenAI embeddings model. If your use case is quite general, so we are not talking about a healthcare specific vocabulary or very profound and complex financial vocabulary, this embeddings model is fine. Because now this is another thing that it's super important. If your use case is for healthcare, very likely you are going to need a model that has been trained for healthcare vocabulary. So what do I mean by this? So imagine that you are working on healthcare and the type of users that are interacting with your application are doctors. Likely you need an embedding model that is able to detect that a myocardial infarction is the same as a heart attack. And this is a very simple concept, but you can imagine if you go to very specific terms in pharma, if you try to match these terms with a model like the one provided by OpenAI that is not specific for healthcare knowledge, each embedding will be very different from one another, and the semantic matching will always fail. Okay, so just a point here, this is just an advanced use case, but it's very important that you know about it. In any case, here we're going to use the small one, the one that is 1536 dimension. Perfect, so now we are going to run this test embeddings script that it's going to convert this text, the quick brown fox, blah, 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 into an embedding. So if you go to commands, this command, put it here, make sure you are inside backend folder, this is very important, and just run it. And now we have converted text into an embedding. Here we are just representing the first values, but remember that the length of the real vector is 1536. Perfect, so now that we have our text split it into chunks and we have the embedding for each chunk, the final step of our ingestion pipeline is to store this information in a database. In our case, we are going to use Postgres, and we are going to use an extension called pgvector extension. And this extension is going to allow our Postgres database to also store vectors. So here you have the representation. Basically, we are going to create a table, and we are going to store both the chunk and the embedding associated to it. Let's go back to our code. Here in our storage, we have actually the full pipeline. You will find the class that will allow us to take one Markdown file and automatically chunk it, get the embeddings, and then storing these embeddings and chunks into our database. So this class will be connected to our Postgres and will be able to perform all these actions. Inside this document store, you have this class called document store. So this class accepts the 2 previous classes that we saw, the one that allows us to create chunks from a Markdown file and the one that creates the embeddings out of a text. And actually, just before we get into it, it's very important that we have our database up and running. To spin up our database, we are going to use Docker. So make sure you have Docker Desktop installed. And once you have it, go to the commands, go to this command over here, Very important, just go back to the root folder. So instead of backend, just go to custom rack, because we are going to use this Docker compose dep that will run a Postgres and will also run our backend and the frontend. We don't care about the frontend for now, but in any case, just run this command. Now Docker will create all the layers and will spin up the different services. If we go inside the app and also database migrations, here we have the structure that our tables in the database will follow. So basically we'll have two tables. One documents table that will have a title, a summary, and a summary embedding, and another table that will contain the chunks, and each chunk row will be linked to a document. Okay, so we have the document chunks, we have the content of the chunk, the embedding, and the document ID. As you notice here in the documents, we also have the summary and summary embeddings. And I will later explain this into the retrieval process, but in order to allow filtering, we are going to store a summary of the document in the database. So this way, whenever we create questions, we're also going to use this summary to filter out those documents that we do not care about. In the document store, we have this LLM summarizer that when triggering the store document process, it will call this summarizer generate summary, and this generate summary, it's just an LLM that actually we have it here. It's going to be GPT-4 mini. So we want to use a very small model because we are going to pass all the content to this model, like the 180 pages, and we just want to extract a brief summary. So we want to use a fast model and a cheap model. You can also use Gemini Flash or one of these small models. In any case, this is just a function that calls OpenAI LLM and just take the output. If we go to the summary prompt, is this one. You are an expert, just create a summary. All right. This step was also taken from this article that I mentioned and that you can also take from the link. And then that you can also find it in the description. All right, perfect. So now my Docker is up and running. And actually, if you go to this .m file that you have inside backend over here, you have here the different parameters that you have to use to connect to your database. So now if you open a database viewer, so for example, if you open db-ever, you can here create a connection. Actually, I will show you. Just make sure that you take all these parameters here and you put them here in the connection. And now, if you click here, you should be able to see the database. We have this documents table that have summary, title, and ID, and also the document chunks. ID, content, embeddings, document ID. All right, so now we are going to run this script inside examples, and it's the stored document that will allow us to take any Markdown file that we have inside documents and put it in our database. So let's go for it. Here I will open a terminal. I will go to the comments. Let's store first one document. So actually, if you want to store all of them, if you put the argument all instead of the argument file, you will take all the Markdown files that you have here and they will be stored in the database. Anyways, here I'm going to just store one. No such file. Okay, remember always to be in the backend directory. Now let's run it. It took 22 seconds. And now if we go to our database and we refresh, first of all, let's go to our documents. We have the first document, the title is this one, annual report. We have a summary. So this summary, it's very high level and it misses plenty of details, but it will be very useful to filter out those documents that have nothing to do with the query. So for example, if the user is asking about NVIDIA and we have in our database documents about whatever, let's say, for example, you have an invoice or you have your own bachelor thesis, whatever. This way, the system will ignore those documents. All right, and now if we go to the document chunks, you see here that each content, so that 700 chunks are stored in our database, and next to each chunk we have the embedding. So each of these vectors is 1536 number long. And something important, notice what I was telling before, the hierarchical chunking. The beginning of the chunk will always be where in the file it's located. For example, here we have these last chunks that refer to this regulation section, okay? And here you have that this section, it's one level higher than this other one, than this other one that it's corporate information inside the final rule, while this one is just inside the final rule. All right, so now we have in our database this document. For example, we can now put another one. We can get the commentary of the CFO, for example. So if we put here, this should be quicker. Yeah, it's here. This is way smaller than the previous one. So it should take less than 10 seconds maybe. Yeah, 10 seconds. So here we created 25 chunks, and if we go now to our database and refresh, so we see the title of this document, small summary, very interesting to have the keywords that the LLM thinks it's important, because in the end when users are querying, they use keywords. So if we have a matching with these keywords, the likelihood that this document is selected will be higher. And now inside document chunks, if we refresh, here we have all the chunks that we got for the CFO summary. Now we have our company knowledge base created, and we are ready to ask questions. So this is the second step of the RAG process. It's about context retrieval. So the context retrieval has three sub-processes. First of all, question embedding or query embedding. Similar as we did with our chunks, we want to represent or abstract the meaning of our query. Then we are going to try to get those chunks that we have in the DB and that are related to our query. And finally, out of all these chunks that we are going to select, we are going to pass them through a third model called a Reranker, that its job is to, as the name says, rank each chunk according to how relevant it is to the query. So let's get to it. First of all, the embeddings. As said, we want to represent the user question as a vector, so we know what's this question meaning, and then we are going to compare it to our different chunks. So if we take our previous example, if the user asks if he likes oranges, then the embedding will be somehow represented over here, because here in this question we are not talking about king or queen, so it will be far from this king and queen representation. But we are talking about oranges, so it's a fruit, so very likely it will be closer to the fruit's embeddings. So then once we have the embedding generated, we are going to compare the distance between each chunk, and this way we are going to know that, okay, if those chunks are closer, we're going to select them. Otherwise, if they are too far, we are going to ignore them. And finally, out of all the different chunks and the query, remember that when using a Reranker, you have to pass both the query of the user and the different chunks that you have. And then the output will be the chunks. So let's go back to our code and see how we are going to do this. So I have here this retrieval pipeline inside the retrieval folder that basically we have this hierarchical retrieval. That again, it's a class that, given a user query, it will run all the different processes that we have seen and pass us the different chunks that we should consider to reply to a user question. So actually we can have a quick look. So we create here the class, the hierarchical retrieval. We assign different things. I do not want to get too much in detail into this. I just want you to know that here I have added one thing that will make our system way more powerful, but also it's a bit more complex. And this is the two-stage filtering. First of all, we want to filter out those documents that have nothing to do with our query. we are going to do this stage 1 document filtering. That for the stage 1 document filtering, we are just computing the difference, like the distance between the embedding of our query and the embedding of the summary of each document. So we're going to go to this table here, documents, and we are going to compare the summary embedding of each document with our query. And after that, we are going to filter some of them. So actually, we have here a threshold that, if we go here, the threshold is defined by default. So if the embeddings are closer than 0.3, we are going to assume they are relevant. If not, we are going to discard them. There's no magic number that you have to put here. It's just a matter of adjusting it using trial and error. All right, so in this first stage filtering, we have the documents that we are going to search. And now in the second stage, we are going to do something similar. Actually, let's go here. Okay. We're going to compare also the embeddings. All right. But we're also going to compare the keywords. We're also going to use the traditional keyword matching to make sure that if a user is asking a very specific term that really matches a chunk in our database, we want to extract this specific chunk, because this is something that has been proven, and it is that this hybrid approach of using both embeddings but also keyword matching, it's way more powerful than only using embeddings. Because it could happen that, as I said, the user is using a term that the embedding model doesn't know that the meaning of that term is the same as another term that is a bit different. For example, it could be that the user is talking about a project that the name is K1 blah 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 blah, but if you are not doing the keyword matching, very likely the model will ignore this term that actually is very important, and it will retrieve other chunks that are not that relevant. So with this keyword matching, you ensure when user is asking very specific questions using terms, you will surely get the context that you want. Now, you will notice here that I'm using something called pgronga, and this is also an advanced library that is used for full text search. So actually, if you go to our migrations, I don't really want you to understand this, but just for you to know, here I'm using this pgronga library that will allow me to do this full text search. So it will provide me a score telling me, okay, how many times the user query appears in a specific chunk. And then by combining these two scores, like the distance between our embeddings and the term frequency in our chunks, we are going to build a combined hybrid score. And this is the score that we are going to use to decide whether a chunk is more relevant or not. All right. Something also very particular for pgronga is that it's going to allow what it's called fuzzy search. So if the user introduces a typo, we'll still match the keyword that the user is trying to type. Again, this is a very advanced use case. I will leave it here for those of you that are more technical and want to dig deeper. Let's go back to our hierarchical retrieval. We now have the second stage. So actually, let's go here. So in the search, first of all, we find the document candidates. We then now find out of the documents that we selected, we extract the chunks. And now there is this last step that it's reranking. So as said, in reranking, we are going to use actually this class, the Reranker. In the reranking folder, you have this class that we are going to use a closed model called Voyage AI. It's quite powerful and it's state of the art in reranking. They have many different models, but for example, we are going to use Rerank 2.5. They're actually quite good. And that's it. Here we are just passing both the chunks, the query, and going to return us this object, rerank result, that contains the chunks ordered. Now, something about rerankers. There are as well many rerankers out there. You could use an LLM, and you could provide like the context, like the different chunks, the query, and you could ask LLM to say, hey, please provide me those chunks that are more relevant. There are plenty of techniques. Rerankers are widely used, and they are state of the art. So very likely the accuracy that you get here will be higher. The good thing with rerankers is that you can use them out of the box. You don't have to create a prompt explaining him how it has to rank or whatever. So here I'm using Voyage AI. You can just go here. It's a company that was acquired by MongoDB. And actually, just make sure that you create an account and you put the API key over here. So just take this env example, convert it to env.deb, and just paste your Voyage API here. I'm going to show you with a demo. Go here to Retrieval, and we are going to run this example called interactive search. And it's going to allow us to see, given a query, what are the chunks that are being retrieved. We are not going to generate the response. We are going to just select the chunks. So actually, just go here. All right, just run it. All right, and here we can now ask questions. For example, earnings share 2026. Okay, so now here we have retrieved the 5 chunks, and it has been immediately. You have seen how fast it is. We can get the 5 chunks that are more relevant. And if we have a look, the first chunk that is considered more relevant is this one, because not only from a semantic point of view, it's close, like 0.5, but also it has the keywords. So if we find here, our query was earnings per share 2026. So earnings per share and the word 2026 should appear many times. Okay. So actually you have here the table, and you can quickly get that the diluted earnings per share is going to be 1.08. We also have another chunk that is a bit less relevant, so it's 0.4, and also less keywords. But for example, you have here revenue for the second quarter was blah, 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 and somewhere here should appear the earnings per share would have been 1.04. So now you can see that with all this information, we can just pass it to the LLM, and the LLM will surely know how to reply because we are giving him the context. So let's try again a different one. For example, let's go here and ask for the executive compensation for the CEO and see what we have. What is happening is that since this query is not talking about NVIDIA or whatever, we have filtered out all documents. So actually we can put NVIDIA compensation. All right, and here we have some, okay, our CEO's fiscal total compensation was, exactly. So here we are retrieving all the different chunks. And the good thing is that we do not only have to select the first chunk, we can pass all these 5 chunks to our LLM, and it will be able to use the context that we want. So now the last step of the RAG process is to generate the response. So now we have seen how to take the context, how to extract the relevant chunks, and now we just have to take these chunks and the original user question and pass it to an LLM. To do this, I'm going to use the Assistant UI. There is an open source library built by these guys that are backed by Y Combinator. And the nice thing is that you can connect this to your custom backend, and it's quite simple. So if we go back to our code, actually here, as I mentioned in the beginning, we have 2 folders. One folder is the frontend. It's going to be the application that the end user is going to see and to interact with. And the other thing is the backend. There is this pipeline that we just ran, the hybrid retrieval, and the frontend will be connected to the backend. So anytime we enter something in the frontend, there will be a connection to the backend, and the backend will reply back with the response. So actually, let's have a look at each part. So if we go to the localhost 3000, just make sure you are running Docker. You will see here the application. This is the Assistant UI interface. And actually, if we go back to our code, I'm not sure if you can see this. Let me put this over here. Yeah. So if you open, just close the backend, if you open the front end, this is a Next.js project, and I just created a page. Inside the page, I just put this component that you will find it in features chat. And this chat is just a component provided by Assistant UI. And it allows me to connect this to my backend, that my backend will be running on localhost 8080, and there will be this endpoint chat. Now, let's go to our backend. So in our backend, what we have to do is to create a server and just put an endpoint that every time it's called, the hybrid retrieval pipeline is run. Remember that the hybrid retrieval pipeline that we just saw, it only extracts chunks. So we just need one last step that will be using an LLM to generate the response. And actually, if we go inside backend, in the main PI, we have here the backend, but now just go to API roots, and here we have this chat API that will be the one called by the frontend. Here we are just processing a bit the request received by the frontend, but here we are running this function called process message event that will run the search function that we just saw from the hierarchical retrieval. Okay, so here we are initializing the class, we are passing some parameters. Here we are running the search function, and the last step that I was mentioning, it's passing these chunks, all these chunks that will be retrieved from the search into an LLM. And actually, this is done over here. We are passing both the question and the chunks to this agent that actually it's not an agent, it's just an LLM. Actually, if you go to here, inside agents replier, you just see we are using GPT-4o, and we are just using the system prompt, that the most important thing is explaining a bit that it has to reply to the user answer. We want this agent to always provide the reference to the document. So this way, whenever we ask, the agent is going to tell us, okay, this is retrieved from this document. So let's go back. And that's it. Once this process finishes, we reply back with the response of the agent, and then the front end will be responsible for printing this. So let's go back to our assistant UI, and now we can run the same queries that we were running before. So this way you see for the same scenario how it behaves. Earnings per share, NVIDIA 26. So now, and it's quite cool because you see like the interface taking care of everything, like loading states and all stuff. So here we see that actually it makes sense, the reply. It seems we do not have information because as of today, the moment we are recording this video, we are October 2025. But it's cool because you see it's not hallucinating. And this is something very important, that the AI doesn't invent information. Every single question that is replied, it's backed with a source. And here is telling us, okay, I have just looked at the annual report 2025. And for that year, the earnings per share were reported were 297 basic and 294 diluted. And actually it's even telling us that this is only for January 26, 2025. So let's do the second one, that was compensation. Again, here is providing all the information. Receive a total compensation of blah, blah, for fiscal year 2025. That's a nice compensation, actually, 50 million. All right, and here again, very important, it's providing us the source. So let's try to ask a question that could be potentially found in the other document that you have indexed in our database. Let's go out to DB, rack documents. It was the commentary of the CFO. For example, I think there was a table here. Maybe let's say what's the revenue per segment during Q2. Let's see if we are able to get this one. Q2 2025. NVIDIA. 26 billion and 3 billion. And document, commentary CFO. So actually, okay, it's here. 26 billion, 3 billion, and the total. This is super nice because as you see, the AI is able to detect information that we have inside tables. So this use case might be a bit redundant because this is open information and you will likely not ask this type of questions to your business, but I'm pretty sure you have plenty of data from your customers or your operations stored in tables. And with this, you're able to quickly access to this information. And most importantly, you can be 100% sure that this is not invented. Till here the video, I hope that now it's way clear for you what it actually is behind the RAG system and how to build a proper one. Now, it's important to mention that what you saw in this video is just a blueprint for building a RAG system. But in order to make a system very accurate, you have to adjust it to the type of questions that you want to answer and the type of data that you have in your systems. So as I said, we are offering a free audit at Flowhog that will serve you to understand where it actually makes sense to integrate AI and how to do it. So feel free to connect with me and let's discuss.